Alright, hey guys, I was sorry for the last video cutoff for this integral of the e to the negative x squared dx video. But in the very end of my previous video, I was talking about how this integral describes the area of this function just on the x-axis. And here, this integral, e to the negative y squared dy, describes the integral along the y-axis here. And we can see that these two values actually are the same. These two values are the same. Although the units of area versus volume are different, when we multiply them together, we actually get the total volume underneath the function. So that is why we could do say these two generate the same value. And so, in this case, we know that our domain was squared. And the y and x-axis are orthogonal. So, in this case, if let's say we had to do I squared again, we could bring these two integrals together because the domain was rectangular. And so we could use Fubini's theorem to bring them in together into just one double integral. This is because we have a rectangular domain, so it makes things much easier. If you notice here, this is just the domain that is projected from f of x, y right here. So these two dotted lines are the same thing. And there's one more thing that's important to consider. If you look at this function, f equals to e to the negative x squared plus y squared, at the tail ends of the function, here, 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 and here, it converges very smoothly, so it approaches the axis pretty fast. That means that we can use this and convert it into polar coordinates. So because they converge smoothly, we can convert to polar coordinates without any error. So let me just erase all of this, and I'll show you what's going on. So here's our y, and here's our x. Again, I'm going to redraw this based on the picture here, but this time I'm going to include a polar area. So here's our rectangular domain here. Nothing has changed yet. Now, let's think about converting into polar coordinates. So, for simplicity, let's choose a circle. Choose a circle right here. Now, we've noticed that if we choose a circular domain, we still have all these missing areas. But that's actually okay, because since we're going from negative infinity to infinity, so our minus a and our a are pulling apart to infinities, and because the function converges at the end smoothly, the missing area basically doesn't matter. So we can get the same answer by converting to polar coordinates. That's why we could do That's why we could have done this, because this function allows us to do this very easily without any change in the values. And just to clarify on one last thing, although here's our y and here's our x and here's our circle, and it looks a little ovalish, but it doesn't matter. If this is our radius and this is our theta, going from 0 all the way to 2 pi, so it does one complete rotation. From our perspective in the xy plane, it looks like a circle. But from the perspective of the domain in the theta and r axes, let me draw it right here. Here's 2 pi. The domain is still actually square from the perspectives of the coordinate system in r and theta. Here, I didn't draw the final boundary because we're letting r go to infinity. But I drew the boundary for theta because we're letting it go from 0 to 2 pi only. And so in this case, the basis is still orthogonal and the domain is still rectangular. Because the domain is rectangular, that means if we need to, we can use Frobenius theorem again to pull out, and because the function is only of r in the middle, so it is a separable function. That is why we could do this. So that is why we can separate the integrals in the final step. I hope this video helps in helping you solve this integral. Know how to solve it on the test, and good luck.